Fluorescence is rare in condensed phases. This is because of the increased deactivation by collision with solvent molecules. It is well known that collision frequency is much higher in condensed phases because of what's called enveloping, where molecules colliding are surrounded by molecules of solvent and therefore made to collide many more times they would have done if they were in a gaseous phase before they break through the envelope. There are a few examples, however. Let's look at this table and subheading solution, absorbed radiation, and emitted radiation. The first one is fluorescein. It absorbs in blue and radiates in green. And this is in its solution in water. Rhodamine B, also in water, absorbs in blue or green or red and will emit in red. Mean radiative lifetime of fluorescence. This is the time taken for fluorescence to fall to 1 over the eth of its initial value, where eta is the extinction coefficient. 1 over E is in moles per cubic meter. Let Kf equal the first order rate constant for fluorescence process. N equals the number of excited moles. dN by dt, therefore, is equal to minus Kfn, which we can rearrange and integrate, and we will obtain N is equal to N naught e to the minus K of t. Rate of emission Q is equal to minus dN by dt, which is equal to Kfn naught e to the minus K of t, which implies Q is equal to Q naught e to the minus K of t. Hence, we can calculate tau naught, and tau naught is of the order of 10 to the minus 9 seconds. The observed lifetime are smaller because of the deactivating process, i.e. the actual lifetime tau is less than tau naught, and tau is equal to 1 over Kf. How do we measure fluorescence? We measure fluorescence by measuring its lifetimes. Here we have got modulated light source, which is sent to the sample and to a variable delay. On the other side, we also have a reference beam which goes through there and goes to the detector here, where it meets the one that went through the sample. And from there, from the detector, it goes to the meter or the computer. Use fluorescence spectroscopy. Select a wavelength of both source and fluorescence radiation lambda s. Keep one constant and vary the other. Now let's look at phosphorescence. Here we've got two cases. Singlet S0 to singlet S1 or S2 or S3. Fall back and you have got fluorescence. However, there are times when we move from here, the electron changes its spin. It is a forbidden process. Now, when it changes its spin, then we go to triplet state. And getting back from the triplet state to the singlet S0, we get phosphorescence. So in this case, spin is conserved, hence S is equal to naught. Here spin multiplicity, then M, defined as M equals 2S plus 1 is equal to 1. That is a singlet state. Whereas on the other side, spin changed. So S is equal to plus 1. By definition, M is equal to 2S plus 1, which therefore in this case gives us 3 triplet state. That is the triplet state. That is spin angular momentum S and orbital angular momentum L couple. In this case, they give energy levels here, and just one only, and yet on the right hand side here in phosphorescence, they give 3 energy levels which are very close together. Lifetime for phosphorescence is longer, is of the order of 100 seconds to 10 to the minus 4 of a second. The wavelength of phosphorescence is longer than that of fluorescence. The process is preceded by S to T1 intersystem crossing, as we showed in the diagram, T1 to S0 phosphorescence. The process S1 to T1 is 10 to the 6 to 10 to the 9 times faster than that of T1 to S0. These forbidden transitions are aided by spin-orbit coupling effects. This is because there is a small energy gap between the S1 and the T1. Fluorescence, transition from excited singlet state. Phosphorescence is transition from the triplet state. Let's have a quick summary here. S0 plus H nu, we go to S1 or S2 or S3, that is excitation. S2, S3 to S1, internal conversion. S1 to T1, intersystem crossing. S1 to S0 plus H nu is fluorescence, whereas T1 to S0 plus H nu is phosphorescence. S1 plus Q is equal to S0 plus Q plus kinetic energy.